Hello everyone, my name is Kerem Gülleroğlu. I'm an electrical and electronics engineering student at Bilkent University, and today I will be showcasing my EEE-102 Introduction to Digital Design term project. So let's begin. My project was to create John Conway's Game of Life with the addition of age mechanics on the Basys-3 board. Now, before I showcase some examples of my project, I wish to talk about John Conway's Game of Life. Conway's Game of Life is a cellular simulation which takes on a plane divided by orthogonal lines, where every divided cell has two states. It's either dead or it's either alive, and its next state is determined by itself and the cell surrounding that cell. The rules can be boiled down to three statements. If the surrounding cells are either 0 or 1, or it is 4 and more, in the next state the cell will be dead. And if the cells surrounding the cell have exactly 3 alive cells, the cell will definitely be alive in the next state. And if there are 2 cells alive surrounding the cell, then the cell will continue as it was. That is, its state will not change in the next state. As such, many interesting and different structures have been found with 3 main categories actually. The still lives, the oscillators and the spaceships. Also, there are other structures which cause infinite growth. Now, some of these functions of course change when you introduce age into the equation, because for one, age means that there will be death from natural causes, and two, age means that every cell now is represented by its age, other than if it's alive or dead. As such, we will not just see black and white squares on a grid, but rather colorful squares. Now, our first example is the infinite growth example, and it looks like this. This structure starts the infinite growth. Now, to run this, we use commands from the Basys-3 board. That is, each switch and button have a purpose to control the game. Now, the first one here is to run the process. Is this. As you can see, the cells change color as per their age, and they spread and they die as it is natural to the game, to this game. Now, another function we have is to pause this process, which is the third switch from the left. As you can see, the entire process is frozen in this state, and it can then be restarted with like this, and it continues on until the time limit is reached, that is, which is 255th cycle. So it has a long way to go. Of course, you'll realize that some of the cells that are not supposed to be dying in the original game are dying. That's because they reached the age limit and unfortunately pass away. So I believe it dampens the cellular growth compared to the original game. Now another thing that we can do is zoom in on certain quadrants, which we do by flicking the force switch, and then using the directional buttons we can change the quadrant we are looking at. This is the first quadrant, this is the second, this is the fourth, and this is the third. As we zoom out, you can see how it works. Now, you can also change the starting grid size, because this process is playing out on a grid of size 32 by 32. And you can also do this on a 16 by 16 grid. The second switch allows for that, and the fifth and sixth switches, of course, change the age and time limits. I think soon the process will reach an end. But other than that, this is basically a standard version of the program. Now, let's study some of the more interesting, shall we say, structures, starting with the glider. This is the glider, and to set this, you have to toggle the correct cells, and well, you select the cells using the 10 switches, the remaining 10 switches. The rightmost 5 tell you which x coordinate you are at. So x0, y0 will be the leftmost, left uppermost corner of the screen, and you set the grid by pressing the center button like this. As you can see, this indicates the lighting up of the left uppermost corner. So let's just get rid of it, and now let's run the glider up. The glider, as you can see, is a diagonal moving spaceship. Now, one interesting thing that occurs with the glider is, as you'll probably guess, still lives aren't actually feasible in with age, because they all decay and die eventually. But when the glider hits a hard wall, it generates an interesting square, as you can see. Now, this is basically the aged version of a block, still life that can sustain itself indefinitely. And other than that, there is not much to add to this. Now I will show you how what is called the pulsar, which is a 3-state oscillator, act in this rule set. This structure that can be on the screen is what is basically a pulsar starter. When it is run, after some time, it will create a pulsar. Now, one thing about the pulsar oscillator is that it depends on some static cells. So, interestingly enough, it will only work for a certain amount of time, as can be seen, and then it will be lost. So basically, some oscillators act like this. They do not oscillate for indefinitely, and as such, some of them have lifetimes. Now, interestingly enough, one other oscillator that will be studied next, which is the pentadecathlon, an oscillator with 15 cycles, doesn't have this property. Now I will show you the pentadecathlon. This is the starting position for the pentadecathlon. Now when we start the process, you will see that it will cycle to the start after passing through 15 states. Now, as I've stated before, this oscillator actually oscillates indefinitely, as it is constantly changing which cells are alive and which cells are dead. As such, it doesn't get much affected from the aging. On that note, in many cases, as it can be seen, the dynamic structures work, and static structures do not work when compared to the base rule set of John Conway's Game of Life. And on that note, thank you for listening.